A raindrop looks simple from far away, but under a rain macro lens, it becomes a tiny archive of the air itself. Every drop begins with a secret. Water vapor cannot usually become liquid on its own. It needs a tiny surface to gather around. That surface may be dust, smoke, sea salt, pollen, or even microscopic biological material drifting invisibly above the ground. So the next time a storm rolls in, the question is not only where the rain came from. The deeper question is, what was floating in the sky before the rain arrived? Rain begins long before a drop falls. Warm water evaporates from oceans, lakes, soil, and leaves, becoming invisible water vapor. As air rises and cools, that vapor reaches a point where it wants to turn back into liquid. But here is the key detail. In the real atmosphere, this almost always happens on a tiny seed called a condensation nucleus. Without that microscopic support, cloud formation becomes far more difficult. The atmosphere is full of these seeds, even when the sky looks clean. That means rain is not just water returning from clouds. It is water negotiating with the entire airborne world around it. Short pause. These seeds are called condensation nuclei, and they are everywhere. Dust particles, aerosol droplets, and tiny fragments of matter give water molecules a place to gather. In a cloud, millions of these particles compete as water vapor condenses onto them. Some nuclei are excellent at this job because their surfaces attract water strongly. Others work less efficiently, but still matter. This is why the chemistry of the atmosphere is so important. A cloud is not just a mass of vapor. It is a crowded, microscopic marketplace where invisible particles decide which droplets survive, grow, and eventually fall as rain. Even air that seems clean is rarely empty. It contains floating dust, salt, soot, plant fragments, and countless microscopic leftovers from daily life. Some come from natural sources, like waves breaking at sea or soil lifted by wind. Others come from human activity, such as traffic and industry. The point is not that the atmosphere is polluted all the time, in the dramatic sense. The point is that it is always filled with material. Air is not a blank space. It is a moving suspension of invisible matter, and rain begins inside that suspension. One of the biggest natural sources of nuclei is ordinary soil dust. Deserts can launch enormous plumes of mineral dust high into the atmosphere, and strong winds can carry that material across entire continents and oceans. These particles are small enough to float for long periods, yet large enough to influence cloud formation. Soil dust can change how many droplets form in a cloud, and even affect how bright or long-lived that cloud becomes. What began as dry ground can become part of a storm hundreds or thousands of kilometers away. That is a remarkable journey for something as simple as dirt. Dust is not the only traveler. Bacteria and other microorganisms can hitch a ride on air currents and end up inside clouds. A bacteria microscope image makes this idea feel almost unreal. Life itself can become part of the atmosphere. Some microorganisms are lifted from soil, plants, water surfaces, or snowfields. Once airborne, they may survive for surprising distances before settling back down. In some cases, their surfaces help water droplets organize around them. That does not mean microbes are controlling the weather. It means the boundary between biology and meteorology is far thinner than it seems from the ground. Then there is pollen. Every spring, enormous numbers of pollen grains are released by plants and carried upward by wind. Most people think of pollen as a seasonal nuisance, but in cloud chemistry, it is another form of floating matter that interacts with moisture. Some pollen grains have coatings that absorb water, which makes them surprisingly active in the atmosphere. they can influence how quickly droplets form in certain conditions. In other words, the forest below is not separate from the cloud above. The two are connected by tiny particles that travel through the air and quietly shape the weather. Smoke and soot are another major part of the story. When wood burns, wildfires spread, or industrial combustion releases particles, the atmosphere receives a fresh supply of tiny carbon-rich fragments. These smoke particles can serve as droplet nuclei, changing how clouds develop. Some are small enough to remain suspended for long periods, drifting far from the original source. This is one reason fires can influence weather patterns well beyond the visible haze. The particles are not just leftovers of burning, they become active participants in cloud formation, altering the structure of the sky itself. Over oceans, wave action throws seawater into the air as sea spray. When the water evaporates, it leaves behind tiny sea salt particles. These ocean aerosols are especially important near coastlines, where they seed clouds efficiently. Salt attracts water very well, so droplets can begin growing around it with ease. This is one reason marine clouds often behave differently from inland clouds. The ocean is not only a reservoir of moisture, it is also a machine for making atmospheric particles, constantly launching invisible ingredients into the lower sky. Cities add another layer. Urban smog contains a mixture of fine particles from vehicles, industry, heating, and construction. Some of these particles can increase droplet numbers in clouds, while others can change how quickly rain forms and falls. The result is not always simple. More particles can mean more droplets, but not always larger droplets. In some cases, clouds become crowded with too many tiny droplets, slowing the process that leads to rain. So modern rain chemistry is partly a story about the atmosphere responding to human-made aerosols. The sky is not isolated from city life, it absorbs it. Inside a cloud, everything begins with tiny droplets. Water vapor condenses on particles, creating cloud droplets so small that they can remain suspended for a long time. Storm clouds are built from billions of these droplets, each one competing for water and moving with changing air currents. As droplets collide and merge, some grow large enough to overcome updrafts and start falling. That is the beginning of rainfall. The cloud is therefore not a static object, it is a living process, constantly rearranging microscopic water bodies into something big enough to reach the ground. Why do droplets need surfaces at all? Because water molecules are strongly attracted to one another, but they still need a starting point in the real atmosphere. A water droplet tends to form more easily when a particle gives it a first foothold. Surface tension then helps the droplet hold together once it begins. Without that foothold, condensation is much less efficient. This is why the smallest dust grain can matter so much. It offers water a place to begin organizing. One invisible surface can change the fate of an entire droplet. This transition from invisible vapor to visible cloud is one of the most elegant changes in nature. Water vapor itself cannot be seen, but once countless droplets grow to the right size, sunlight scatters from them and the cloud becomes visible. A cloud sky is therefore not a shape made of empty mist. It is a crowd of tiny liquid spheres suspended in air. Condensation turns the atmosphere from transparent to textured. The moment is so ordinary that people rarely notice it, yet it is the exact point where weather becomes visible to the human eye. At the microscopic scale, the ingredients of rain are astonishingly small. Many nuclei are measured in micrometers, which means thousands of them could fit across a single grain of sand. Microdust, salt crystals, pollen fragments, soot, and biological material all sit near the limits of what the eye can ever notice. A microscope reveals a world where shape, texture, and chemistry decide weather outcomes. What looks like empty air is really a dense field of tiny surfaces. Rain begins in a realm where size is almost everything. When scientists collect rainwater samples, they rarely find perfectly pure water. A rainwater sample can contain dissolved gases, trace minerals, and suspended particles that reveal the path the drop took through the atmosphere. Water testing may show differences from one storm to another, depending on location, season, and wind patterns. The important lesson is not that rain is contaminated in a simple sense. It is that rain records the atmosphere with surprising precision. Every collection jar becomes a small history book written in water. A simple field experiment makes this easier to understand. Place a clean beaker outdoors during rainfall and let it collect water directly from the sky. Then compare it with distilled water kept in a sealed container. The two may look similar at first, but the rain sample usually contains more dissolved and suspended material. This does not mean the sky is dirty in a dramatic way. It means rain has traveled through a chemically active environment. The beaker becomes evidence that falling water is never entirely disconnected from the air it passes through. Filtration offers another clue. Pour a rainwater sample through a water filter, and tiny solids may remain behind. Under laboratory test conditions, the filter can reveal material too small to notice by eye. Some of it comes from natural dust, some from ocean salt, some from combustion particles, and some from the city air above. Filtering does not prove that rain is unsafe. It shows that raindrops often carry a visible trace of the atmosphere's suspended ingredients. What survives the filter is a reminder that the sky is always in conversation with the ground. A microscope slide takes that idea even further. Under a lab microscope, rain residue can show irregular grains, salt crystals, soot fragments, and biological traces. Each sample tells a different story depending on where the storm formed and what air masses it crossed. A single slide can reveal the fingerprints of the local environment, and sometimes distant regions too. The droplets themselves may be temporary, but the particles they carry are often the opposite. They persist, travel, and document the journey. If rain is collected over a forest, a field, or a city, the composition can differ noticeably. City rain may contain more combustion-derived particles and urban aerosols. Rural rain may reflect more soil dust, pollen, and natural organic material. Over forests, biogenic particles can become more important. The comparison is powerful because it shows that rain is not universal in a simple way. It is local weather shaped by regional air history. The storm above a rooftop is also a survey of everything the wind has carried into that sky. Altitude and weather systems change the recipe again. Mountain clouds may form in colder, thinner air, while warm coastal storms interact with sea salt and ocean spray. Weather radar can show the size and movement of storm systems, but the chemistry inside those systems depends on the particles present in the atmosphere. Strong updrafts, temperature, humidity, and pollution levels all influence what ends up inside the drop. A raindrop falling from a mountain cloud does not share exactly the same history as one falling over a coastal city. And yet, rain is not something to fear as a category. Fresh rain can still be natural, nourishing, and essential for life. Plants depend on it, rivers depend on it, soil depends on it. Even when particles are present, rain remains part of a larger system that supports ecosystems. The presence of airborne material does not cancel the usefulness of rain. It simply reminds us that nature operates through mixtures, not perfection. A rain puddle is not a symbol of impurity. It is evidence that the atmosphere is doing its job in a very complex world. This has environmental meaning far beyond the raindrop itself. The particles found in rain connect directly to air quality, ecosystems, and climate behavior. Aerosols can influence how clouds reflect sunlight, how long they last, and how precipitation forms. In that sense, rain is not only water returning to Earth, It is also a transport system that moves clues from the atmosphere back to the surface. Environmental pollution leaves traces, but so do deserts, oceans, forests, and living organisms. Rain gathers them all into a single event. That is why rain acts like a messenger. Every storm carries evidence of air quality, ocean spray, soil dust, smoke, pollen, and microscopic life. Scientists can read those clues to understand what happened in the atmosphere before the rain arrived. It is a kind of chemical storytelling. The sky writes in particles, and rain delivers the message. Even a single drop can help reveal whether the air was coastal, rural, smoky, dusty, or urban. The atmosphere is always speaking. Rain simply makes the message easier to collect. So the final takeaway is simple, but not simplistic. Every raindrop tells a story. It begins with invisible vapor, gathers around a tiny particle, grows inside a cloud, and falls, carrying traces of the journey. Some traces are natural, some are biological, and some reflect human activity. A water drop is therefore not just H2O in motion. It is a record of the sky, the land, the ocean, and the living world all at once. That hidden complexity is what makes rain so scientifically beautiful. After learning this, rain is harder to ignore. A storm rain against the window is no longer just weather. It is a moving sample of the atmosphere, collected drop by drop in real time. Looking at a rain window becomes an invitation to wonder what invisible particles the wind is carrying today, and what history is being written overhead. If this kind of science changes the way rain is seen, the best next step is simple. Keep watching the sky, keep asking questions, and keep noticing the hidden world inside ordinary things.